Alright, welcome back. This is CWI Tutoring. Today I'm doing a derivation of the parallel axis theorem so that we can better understand where it comes from. To start out, I've got this picture drawn where I have some rotational axis about which we're going to measure the moment of inertia. Now remember, similar to mass, moment of inertia is the same for a configuration, whether it's spinning or whether it's staying still. In other words, if you have a flywheel that's spinning and you go to try to stop it, it will have the same moment of inertia as if you were to try to start moving it, right? For a large flywheel, that moment of inertia is going to be higher because the moment of inertia has to do with how far the mass is from the rotational axis and then how much the mass weighs itself. I'll go ahead and write this up here. So you remember the formula for moment of inertia is this, or at least for particles. So this is the moment of inertia, I equals the sum over all the masses of the system. That's from the first mass all the way up to the nth mass, if you have n particles. And so if I wrote that out in long form, it would of course be, or wait, I'm going to write this out long form, not in sum form, so this might be m1 times r1 squared plus m2 times r2 squared plus dot 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 for as many finite number of particles as your system has. So I wanted to show, so here's the moment of inertia axis that we're going to take a look at for this two mass system configuration. I've put this this axis at the center of mass, and that's important because you'll remember that the center of mass, we'll say it's in the x direction, is equal to the sum from 1 to n masses of mi ri divided by the total mass of the system, which is the sum from the first mass to the nth mass of m sub I. So this would be m1, m2, m3, and 4, r1, r2, r3, r4, etc. So we know that dividing by zeros is a problem. What I'm going to go ahead and do is I'm going to exploit this, and I'm going to say, you'll notice I've kept this plane flat. So in other words, m1 is on the same plane as m2, is on the same plane as ICM, and this other one here. So what's nice about that is I've simplified it down to one axis, which I'm calling the x-axis. But this also works for any number of different directions, you know, configurations in 3 dimensions as opposed to just 2. But I'm going to stick with this one and then extrapolate the theory to 3 dimensions. So I know I can't divide by 0, and I know that there's no way that I'm going to have 0 mass if I have 2 particles, right? Because the sum here of mi is just m2 plus m1. So I'm going to set my rotational axis at x equals 0 when it's at its center of mass. So x hat equals 0. Well, I know that the sum of masses can't equal 0, so I can multiply that across to 0. And then what I end up proving to myself is that this sum, the sum from the first mass to the nth mass of mi ri, must equal 0. So that's going to be useful. We'll put that in our pocket and go back to it eventually. So the idea here is I have this, I've calculated the moment of inertia of the center of mass rotational axis. Well, the beautiful thing about the parallel axis theorem is that I'm going to go ahead and say, I'm going to keep my new axis parallel to the old axis, right? These are parallel, but I'm going to move it by some distance. Sometimes we call that distance d. So I'm going to go ahead and call the distance from the center of mass axis to I prime, which means the new rotational axis, or the new rotational moment of inertia about this axis. So I separate them by distance d. Alright, Now I'm going to write some formulas that are going to help us out. Firstly, I'd like to say that, of course, I at the center of mass, the moment of inertia at the center of mass, is the sum of all mi's times ri squared. So this is going to equal m1 r1 squared plus m2 r2 squared, where r2 is the distance, the perpendicular distance, the shortest distance from this center of mass axis to mass 2, and m2 is the mass itself. So now we're interested in how we could maybe shortcut and figure out what I prime is, right? Well, I prime we've moved by a distance d, but of course we'd use the same moment of inertia formula for a point-like particle. The difference here is that the distances are different, right? So instead of r sub I need to write a changed version of r sub I. I'm going to call that r prime sub I, meaning the new radius index. So the trick here is, here's this new axis up here. This is the one we're interested in now to calculate. We're assuming that we already know the moment of inertia about cm axis, center of mass axis. So this new parallel distance is going to be called r2 prime, because it's the new distance from mass 2 to the new axis. And this distance right here from the first mass to the new axis is going to be called r1 prime. Alright, so now I'll write this out in long form and say this is going to be equal to m1 r1 prime squared plus m2 r2 prime squared. Alright, so next what we're going to do is we're going to figure out relationships of how we can relate r1 to r1 prime and distance. So you'll notice here that geometrically it sure looks like r2 plus d, right, because this is the distance that we moved the axis. r2 plus d equals r2 prime. So I'll write that down. r2 prime equals the original distance of mass 2 from the original axis plus d. Likewise up here we can write that r1 prime equals r1 minus d, right? So if I do r1 and I subtract this component out, what I'm left with is r1 prime. So r1 prime equals r1 minus d. Alright, so now I have a system of equations to relate my primes to my originals. So I'm going to go ahead and, now that we see that, I'm going to go ahead and erase the picture because I'll need some room. Hopefully the picture helps to show you how we measure things from the old axis to the new axis and where we get those relationships from. So I'm now going to use my expanded form of the two-mass system, but wherever there's an R1, I'm going to plug in, or wherever there's an R1 prime, I'm going to plug in R1 minus D. And wherever there's an R2 prime, I'm going to plug in R squared plus D. Alright. So we're going to rewrite this and say I prime, or the moment of inertia around the new center of mass, is equal to the first mass times R1 prime, which is equal to R1 minus D squared, right, because we're taking R1 prime squared, plus M2 R2 prime squared, which is equal to R2 plus D squared. Alright, so now we're going to go ahead and factor and group. So here, if you go through the work, you'll find that this is equal to M1 R1 squared minus M2, or minus 2 M1 R1 D. Let me see if I got that right. Yep. And then the final term for this expanded form would be minus m1, or I'm sorry, plus m1d squared. Okay, now I'm going to do this one. I'm going to write it lower down the page so I have more room. Put a little dot, dot, dot here, and then pull it out down here. So this is going to equal to m2r2 squared plus 2m2r2d, and then we have to dot, dot, dot again, plus m2d squared. Alright, now I'm going to go ahead and group. I'm going to box this off. What I'm going to do next is I'm going to put like terms. So you'll notice here I have a term that's m1r1 squared, and I have a term that's m2r2 squared. And let's group those together and you'll see why in a minute. So I prime is equal to m1r1 squared plus m2r2 squared. Let's group these weird middle terms together, the two mrds for the different m's and r's. So that's going to be minus or plus 2m2r2d minus 2m1r1d. Okay, and then we're going to group together our last two terms, the m1d squared and the m2d squared. So we have plus m1d squared plus m2d squared. And I fit it all on the board, which is really nice. So you'll notice that this right here, the m1r1 squared plus m2r2 squared, for the two-particle system is actually I center of mass. You remember that drawing we had? We started at that axis and then we wanted to figure out what the moment of inertia about the new axis was. So we can actually write the new axis in terms of the old axis that we knew. Okay, then here what I'm going to do is I'm going to pull out my 2d, just going to factor that out, 2d, and leave my m2r2 minus m1r1. Then over here, I'm going to pull out my d squareds and leave m1 plus m2 d squared. Yeah, just factor those out. So here's where this little term comes into play. If we do it for the two-mass system, we'll see that 0 equals the sum from I equals 1 to 2 of mi ri. So what that means is that m1 r1 plus m2 r2 equals 0. And then we could subtract this over and say, or we could write it as m2 r2 equals minus m1 r1. And so if we go ahead and substitute into R2 here, you'll notice that these actually cancel out and go to 0. And so what you're left with is the moment of inertia about the new axis, I prime is equal to I center of mass, plus m1 plus m2 d squared. And of course we can write m1 plus m2 as the total mass, big M. And so that's where our parallel axis theorem comes from. So I prime, the new moment of inertia, is equal to the old moment of inertia at the center of mass, plus m times d, the distance, the perpendicular distance we moved the new axis to. So your new moment of inertia is equal to your moment of inertia about the center of axis, plus the total mass of the system, times the distance that the new axis is from the original center of mass axis. So I hope this was helpful. I know it was a bit long, but hopefully it'll help kind of conceptualize what's going on with the parallel axis theorem. Alright, thanks for watching, and I'll see you next time.